There are a number of ways to identify aircraft by type and function. We have already learned about fixed-wing and rotary-winged aircraft in previous lessons. Two of the categories often used to classify flying machines are those that are deemed to be lighter than air and those that are heavier than air. In this section of our STEM instructional program, we will be introducing you to aircraft classified as lighter than air. There are two basic types of lighter than air vehicles that we will discuss in this lesson: balloons and dirigibles. In Section 1 of the STEM instructional program, we introduced you to the four forces that affect the flight of an object: weight, lift, drag, and thrust. In a traditional aircraft, lift is provided by wings and other parts of the structure. As thrust moves the craft through the air, it changes the flow of that air, particularly around the wings, and causes an unbalanced force. The sum of these forces is positive or upwards, which provides lift. The major difference between heavier than air and lighter than aircraft is how lift is provided. Lighter than aircraft are designed to contain a large volume of gas that is less dense than the surrounding air. This less dense gas displaces the surrounding heavier air and floats on the air just like a cork does on the water. In the case of the lighter than aircraft, the unbalanced force caused by the lighter than air gas would provide lift. To begin our study of the concept of lighter than air, we need to review the three primary states of matter: solids, liquids, and gases, and how particles, either atoms or molecules or both, are arranged in each. In each of these states, particles are able to vibrate within a certain area. The amount of vibration is due to the amount of heat energy contained in those molecules. The more heat energy a particle has, the harder it vibrates, and the more space needed to vibrate. A solid is typically defined as an arrangement of atoms or molecules that have a definite shape and volume. In a solid, the particles are packed together closely, typically in a lattice or crystal structure, and have the least amount of heat energy of the three states. Because they are closely packed together, solids are considered to be incompressible. Substances remain in a solid state even with the addition of heat energy until they reach their melting point, at which the solid structure starts to break down, and particles are allowed to move around each other. A liquid is an arrangement of particles that has a definite volume, but can change its shape to take the form of any container that it is in. This shape change is due to the particles, while still linked to other particles, being able to move around each other. As there is still little space between particles, liquids are also considered to be incompressible. Because of this ability to change shape while still being incompressible, liquids are often used for hydraulic functions, such as aircraft landing gear. Substances maintain liquid properties even with the addition of heat energy until they reach their vaporization temperature. At and above the vaporization temperature of a substance, the particles have collected sufficient energy to cause them to vibrate hard enough to break any connections to other particles. This allows them to independently move in any direction until they collide with other particles or the walls of the container. At this point, the substance is considered to be a gas. A gas is an arrangement of particles that takes the shape of the container holding it and also expands to fill up the entire volume of that container. Gases have the highest amount of heat energy of the three primary phases of matter. As the particles collide and bounce off the walls of the container, they exert an outward pressure on that container. The pressure on the container can be increased by either adding more particles or by adding additional heat. As there is a larger space between the particles than in solids and liquids, gases can be compressed. This can be accomplished by physical pressure, as in a piston, or by the cooling of the gas. Long before the Wright brothers' famous flight, Early aviation pioneers experimented with lighter-than-air craft and proved that controlled flight was within reach. From ancient times, the Chinese have understood that hot air rises and have applied the principle to a type of small hot air balloon called a sky lantern. A sky lantern consists of a paper envelope, under or just inside of which a small lamp is placed. Sky lanterns were traditionally launched for pleasure and during festivals. Such lanterns are known in China from the 3rd century BC. As it is this oldest and simplest lighter-than-air craft, we will use it to discuss the basic theory of hot air balloons. The basic theory of the sky lantern is common to all hot air balloons and obeys Charles' law, also known as the law of volumes. What the law says is if a gas is heated, it will expand. If it is cooled, it will contract. For our sky lantern, the air inside the bag and the air outside are initially at the same temperature and the same density. When the flame is ignited, the air molecules nearest the flame absorb the heat energy, vibrate harder, require more space in which to move, and also start to rise. This forces some of the other particles in the bag to be pushed out. It also brings other cooler molecules in contact with the heat source. They also vibrate harder, start to rise, and push more of the cooler molecules out of the bottom of the envelope. As more particles gain energy, they vibrate harder, the overall density of the gas in the balloon decreases, and the balloon starts to rise. Eventually, the entire envelope is filled with high energy particles. The envelope is much less dense than the surrounding air, and the balloon ascends. These fast-moving particles cool when they touch the outside surface, lose some of their energy, and move downward. When they again come close to the heat source, they gain the lost energy and rise again, setting up a circulation of hot air in the balloon. Thus, hot air surrounded by cold air will rise. It simply displaces a volume of colder air that is heavier than itself, thus providing positive lift. If hot air is trapped in a balloon envelope, it will generate lift because the air inside is actually lighter or less dense than the cooler air outside. From the lesson on lift, we also know that the atmosphere that surrounds us is not constant. The air is most dense closest to the surface of the Earth, and less dense the higher we get in elevation. This would have an impact on any lighter-than-air craft. The lighter-than-air craft would rise until the density of the gas inside of the envelope is close to that of the atmosphere outside of the envelope. So the lifting capacity of an airship is equal to the buoyant force minus the weight of the airship. These factors would also determine the altitude that can be achieved. The altitude at which an airship can fly largely depends on how much lifting gas it can lose due to expansion before a state of equilibrium is reached. The history of lighter-than-air flight began with the first hot air balloon, built by Joseph and Etienne Montgolfier in France. In 1782, the brothers constructed a large balloon, which they filled with hot air produced by an ordinary bonfire under the balloon. The balloon rose more than a mile into the air. A year later, they sent up a second balloon, this one carrying a tub that held a duck, a rooster, and a sheep, the first aeronauts. Then only 2 months later, they constructed yet another balloon, this one large enough to carry a human into the atmosphere. There are 2 major problems with hot air balloons. The first is that you needed to maintain the heat source to keep the envelope filled with warmed air. Early hot air balloons were heated by a fire located under the balloon. When the balloon took off, it would leave the heat source behind. If the heat source is turned off, the air in the envelope will cool, increasing its density. As it contracted, it would bring in additional cool outside air, and the balloon would descend. A solution to that issue would be to try to find a way to attach or carry the heat source in the balloon. In the early 1900s, Louis Goddard invented a petroleum burner, but it was not efficient enough to give lift to hot air balloons. In the early 1960s, the modern propane burner was developed, and with it, the introduction of the modern hot air balloon. Another possible solution would be to fill the balloon with a gas that was itself lighter than air. To examine this concept, we need to look at the periodic table of elements. The periodic table is an arrangement of the known elements. In the example of the periodic table displayed here, as you move down and to the right, the elements become heavier. Up and to the left, they become lighter. The elements shown in red are gases at room temperature. Black are solid, and blue elements, such as bromine and mercury, are liquid at room temperature. Some elements are not found in nature and have been man-made. Looking at these periodic table trends, the only two practical lighter-than-air elements that are gases at room temperature are hydrogen and helium. Nitrogen, while lighter than air, is not a practical lifting agent, as 78% of the atmosphere surrounding us is nitrogen. While not the only substances that can be used, hydrogen and helium are the primary lifting gases used in lighter-than-air craft. Hydrogen, the lightest element, is also one of the most reactive. A hydrogen atom cannot exist by itself. In its purest form, hydrogen molecules are formed by two hydrogen atoms connected together. Hydrogen gas forms explosive mixture with air in concentrations above 4% and with chlorine above 5%. The explosive reactions may be triggered by spark, heat, or even sunlight. As such, it is a great fire hazard and a serious explosion hazard in large quantities. The Hindenburg disaster is frequently cited as an example of the safety risks posed by hydrogen. Because the hydrogen molecule is very small, it can easily diffuse through many materials, such as latex, so that the balloon will quickly deflate. This is one reason that many hydrogen or helium-filled balloons are constructed out of non-porous materials, such as mylar. Helium is the second lightest gas and can exist as individual atoms. For that reason, it is an attractive gas for lifting as well. A major advantage is that this gas is non-combustible. But the use of helium has some disadvantages too. As helium's atomic radius is small, it diffuses through more materials than hydrogen. Helium is also very expensive. Although abundant in the universe, helium is scarce on Earth. Helium is produced by the slow decay of radioactive materials within the Earth over millions and millions of years. As such, helium is classified as a non-renewable resource, as it cannot currently be manufactured from other materials. The second issue with lighter-than-air balloons was that, unless tethered to the ground, the balloon goes wherever the wind carries it, and passengers have almost no control over the direction or speed of their travel. The pilot can only control altitude. By the time of the American Civil War, lighter-than-air craft proved to be an invaluable military asset. In the tethered balloon several hundred feet in the air, a military scout could survey the battlefield and observe enemy positions. Additions needed to convert a balloon into a usable aircraft are a method to propel the balloon in any given direction and a rudder with which to steer it. Although inventors were able to make many advancements, the biggest challenge was to find a way to successfully steer the craft. Inventors conceived numerous ideas, some seemingly logical for the time, like adding oars or sails. Others were a little far-fetched, like harnessing teams of vultures. A practical solution to the balloon propulsion issue was found in 1886 when Gottlieb Daimler created a lightweight gasoline engine that could be used to turn a propeller. Modifying the shape of the envelope to make it more aerodynamic and adding steering fins to the rear of the envelope helped solve the direction problem. This modified form of a balloon with these steerable features is commonly referred to as a dirigible. The terms dirigible and airship are synonyms. A dirigible or airship is any lighter-than aircraft that is steerable and can navigate through the air under its own power. Dirigibles are classified either as rigid airships, semi-rigid airships, or blimps. A rigid airship has a rigid framework that maintains the shape and carries all of the structural load, covered by an outer skin or envelope. The lifting gas is contained in one or more internal gas bags, cells, or balloons that are attached to the frame. Rigid airships are typically unpressurized and can be made to virtually any size. The greatest disadvantage of the airship, however, is size, which is essential to increasing performance and load carrying capability. As size increases, the problems of ground handling also increase geometrically. First flown by German Count Ferdinand von Zeppelin in 1910, the vast majority of rigid airships built were manufactured by the firm he founded. After the outstanding success of the Zeppelin design, the word Zeppelin came to be commonly used to refer to all rigid airships. Unfortunately, as with many advances in aviation, the military uses of airships soon became evident. During World War I, the German military made extensive use of Zeppelins as bombers and scouts. While most of the ships were built by the Zeppelin company, not all German airships were Zeppelins. The German military also used rigid airships of very different design built by other companies. Commercially, however, at their peak, Zeppelin-style dirigibles were to carry a maximum of 72 passengers in an elaborate gondola that also held a dining room, bar, lounge, and walkways. The USS Shenandoah was the first American-built rigid airship manufactured for the United States Navy. The Shenandoah was the first of 4 United States Navy rigid airships, the others being the Los Angeles, the Akron, and the Macon. The Shenandoah was constructed in 1922 and 1923 at Lakehurst Naval Air Station and first flew in September of 1923. Unlike other airships at the time, Shenandoah used helium as its lifting gas instead of hydrogen. A blimp, or non-rigid airship, is a powered, steerable, lighter-than-air vehicle whose shape is maintained by the pressure of the gases within its envelope. A non-rigid airship relies entirely on internal gas pressure to retain its shape during flight. If a blimp deflates, it loses its shape. Unlike the rigid design, the non-rigid airship's gas envelope has no structural compartments. It typically has smaller internal gas bags or balloonets. Balloonets are air-filled bags that are located inside the envelope. The blimp has 2 balloonets, one fore and one aft. The balloonets are similar to the ballast tanks of a submarine. Because air is heavier than helium, the balloonets are deflated or inflated with air to make the blimp ascend or descend respectively. They are also used to control the trim or levelness of the blimp. The pressure of the helium in the envelope is adjusted by changing the amount of air in the balloonets. Normally, blimp pilots do not have to add or remove helium from the envelope. However, there is a helium valve on the envelope that can be used to vent helium should the helium pressure exceed its maximum safe limit. The valve can be opened manually or automatically. Goodyear began using blimps to advertise their brand in 1925. Blimps have also played an important role in the armed forces of many countries. The U.S. Navy's lighter-than-air program made extensive use of blimps, primarily in anti-submarine and reconnaissance roles, from the 1920s through the 1950s. The British used this same lighter-than-air technology for barrage balloons and other kite balloons having a streamlined shape and stabilizing tail fins. The spirit of innovation, Goodyear's last true blimp, was retired on March 14, 2017. A semi-rigid airship has a supporting structure, but the main envelope is held in shape by the internal pressure of the lifting gas. The structure supports and distributes loads, provides structural integrity during maneuvering, and stops the envelope from kinking in the middle by distributing the load into the envelope, while also allowing lower envelope pressures. In May of 2011, Goodyear announced it was replacing its fleet of non-rigid airships with 3 semi-rigid airships built by Zeppelin. Although technically incorrect, Goodyear continues to use the word blimp in reference to these new semi-rigid dirigibles. Wingfoot 1, the first such model in Goodyear's U.S. fleet, was christened on August 23, 2014, followed by Wingfoot 2 in October of 2016 and Wingfoot 3 in August of 2018. The end of commercial dirigible travel came in the 1930s as a result of 2 events. One was the continuing improvement in heavier-than-air travel, which made the much slower dirigible obsolete. Over time, airship use decreased as airplanes exceeded their capacities for speed, control, and safety. The other event was the dramatic explosion and destruction of the rigid airship Hindenburg as it attempted to moor at Lakehurst, New Jersey on May 6, 1937. The ever-present danger that the highly flammable hydrogen gas used to inflate dirigibles would ignite and burn had finally come to realization at Lakehurst. Although later dirigibles were designed to fly with non-flammable helium, they never really regained the popularity of the pre-Lakehurst period. Today, dirigibles are widely used for advertising purposes. The Goodyear blimps and airships like them have now become familiar sights at outdoor sporting events all over the United States. That is not to say that the age of airships has passed. Modern airships are used for aerial observation, photography, geological surveying and research, advertising, and tourism. So is there a future for lighter-than-air transportation? There are always the dreamers. Concepts have been proposed that would bring back the golden age of lighter-than-air luxury transportation. It has also periodically been suggested that airships could be employed for cargo transport, especially delivering extremely heavy loads to remote areas over great distances. A roadblock to the large-scale development of airships as either luxury travel or as heavy haulers has been figuring out how they can be used in a cost-efficient way. Perhaps the biggest problem is the cost of fuel. Airships, or at least the non-exploding variety, require large amounts of helium, a rare substance, which can cost upward of $100,000 for one trip. All this raises questions about whether a form of transport depending on it could ever get off the ground.